last the last unit, or the last packet of Unit 8. So this is Chapter 25. We're still talking about capacitance. So we're going to talk about two things: energy stored in capacitors, and then adding dielectrics. So a capacitor, imagine it's two parallel plates with air in between, or in a vacuum. And then now we're going to put stuff in there and see how that affects the capacitance when we fill it with a dielectric. Pretty hefty packet. But in the real world, there's a maximum voltage at which a capacitor can operate it. If you hook a capacitor up to more voltage than what it can handle, it'll blow really loud. It's this really loud pop sound, and then the capacitor is dead. And therefore, there's also a maximum energy that each capacitor can have. But the following derivation is good for any. And what we end up with is a few different ways of expressing Umax. I mean, you can see you can work through that stuff if you want. You don't have to reproduce that. But Umax is 1/2 Q squared over C, or it's also equal to 1/2 QV, or it's equal to 1/2 CV squared. And we get that just by substituting, right? If we put in, Q equals CV, whatever and we get all these different expressions. I would say pick one of these three and memorize it. Just commit it to memory. Stored energy is 1/2 CV squared, or 1/2 QV. Right? You can get the other forms of it just by substituting in whatever you want to do there. So that's it. And then since it's CV squared, C is epsilon naught A over D, and the V is negative ED, as you can see there. It's also equal to 1/2 epsilon naught AD times E squared. And then energy density, I'm not sure if you're going to see this or not, again, but it's here. Energy density is lowercase u, and what it is it's the amount of energy per volume. So it's a density, right? Energy per volume. So if you take this and you divide by AD, the area times the distance, that's the volume of the capacitor. Just think about parallel plate. Actually, this is for all geometries. So you end up with 1/2 epsilon naught E squared. Or again, E is the electric field. Okay, so how does this work now? Let's take a look back. This is example 1, but I think this is the same as another example that we had earlier on. So let's fill out this little chart and see how we do. All right, so using the methods we had before, we're able to get this. The capacitance of each of these, the equivalent capacitance, the stored charge on each of them, and then total stored charge. And then the voltage, and we can see, so then if we calculate CV squared or something like that, 1/2 CV squared, this ends up being 80. This, by the way, is in microjoules. 80, and then 1/2 5 times 4 squared gives you 40. 1/2 10 times 6 squared would give you 180. And then here I end up with 300. Okay, here's the general rule in a circuit. U total, stored potential energy, is equal to U1 plus U2 plus U3, etc. That's the general rule for this. So when you get to the end of this chart, if you're doing a chart like this, when you get to the end, you add these up, and if these add up to this, then you're good. If you add these up and they don't equal the total, then you must have done something wrong. All right, example 2, capacitor's charge, stored energy is 4 joules. The charge distributes, then connected to another one, and so they're in parallel, and then the charge distributes equally. What is now the total energy stored in the E fields. So here it is initially, here it is finally. And so this Q1 is equal to C1 V1. Right? If we connect here a voltmeter, whatever we read there, that'll be the stored charge. Right? And so then U1 initial here is going to be 1/2 Q1 V1. But we want to get this in terms of Q and C because the voltage is going to be changing from one situation to the next. So if I substitute in, I know that V is equal to Q over C, so this is 1/2 Q1 squared over C. Okay, all right, so that works. Now let's take a look at this. This is going to have some voltage. This will have some other, it'll be the same voltage actually. But what we do know is that Q, here's Q1, here's Q2. So for this afterward situation, let's call this QI, initial charge. Q1 plus Q2 is equal to that QI that we had before. And it doesn't say this, but we're assuming also that these are equivalent capacitors. And so then, because we know that because Q1 and Q2 are the same. So Q1 and Q2 are both equal to QI over 2. And so then the two voltages will be the same. We know that because of Kirchhoff's loop rule, right? The voltage here has to be the voltage gained here is lost here, whatever that case might be. So then U2 is going to be 1/2 Q1 over 2 squared. So it's the same thing over C1 plus 1/2 Q2 over 2 squared over C2. And when we simplify this, we end up with, because Q1 is the same, and Q and C is the same also, we end up with is 1/4 Q1 squared over C1. And that's the total energy here. Notice I had more total energy before. I lost some. So question B, where did the excess energy go? It went to heat. As this was discharging, and this one was charging, we had current going through the wires. Those wires heated up. So some of that energy was lost to heat. Energy stored by an isolated sphere. You can see this. Again, I don't think you're going to see this again, but it's worth seeing and working through the derivation. But I don't want to waste time on the video. Let's get to the other thing. Example 3. Okay, here's this really big, crazy circuit. And it's, the question is, all the capacitors have capacitance of 6. All the batteries have a potential of 10. What is the charge on the capacitor C? Now, this looks like a really crazy problem. Like, there's so many capacitors. There's so many, not so many, but a lot of batteries. How would you even do this? Well, here's the thing. Using Kirchhoff's loop rule, which, again, through any path, through any loop, the potential difference gained has to equal the potential difference lost. So there's a potential difference of 0 when you've gone through that whole loop. So the question is, the capacitor that's labeled C, can you follow a path that gets you only that one capacitor and one battery? And there is. There's a path. It's a maze, right? But you can do it. I'm going to hold this up. Can you see it? If you follow that path, then all you do is you go through one battery and one capacitor. That means that the voltage on the capacitor, the potential difference, has got to be 10 volts. And so it's actually really easy. Q equals CV. C is 6 microfarads, and we've got 10 volts. So this is 60 microcoulombs is the stored charge on the capacitor. That's it. Okay, now moving on to dielectrics. Dielectrics is an insulator that is placed between the conductors. The dielectric constant K is a measure of how effective the dielectric is in insulating. And what we do is we put these in to increase the capacitance. There's a letter K, which is really kappa. It's not really the letter K. The kappa is the Greek letter, and what that does is it increases the capacitance. So kappa is always more than 1. And so you can see some dielectric constants there. Air is very close to the vacuum. Vacuum would be kappa 1. And so really what happens is we take, the capacitance changes. That capacitance formula we had, remember we had the seed formula. Capacitance is epsilon naught A over D. Really there's that kappa there. And so that's how we calculate what the new capacitance is. We just multiply, so that would be kappa times C naught. If C naught is the capacitance without the dielectric, just epsilon naught A over D, then we put in this new thing, and that gives us the new capacitance of the capacitor. And actually this is there, right? Kappa times C naught. So let's see what happens when we insert dielectrics to the circuit. So example 1. Capacitor is charged to Q. So by the way, as we're going through this, here are the situations. We can charge the capacitor and then disconnect it, so the charge remains there, and then we insert the dielectric. Or we can leave it hooked up, so the potential difference is remaining the same. Battery is maintaining the potential difference, and then we insert something because we might get some different things going on. So we have a capacitor charged to Q2, Q naught, potential difference of V naught, and holds an energy of U naught. But then the capacitor is disconnected and isolated. So if it's isolated, the thing that's going to remain constant is the charge. And dielectric is inserted, so now we've changed the capacitance. Since we changed the capacitance, well, Q equals Q naught, so that stays the same. V, however, changes. Notice the voltage is going to go down. And so in this little chart here, example 1, C goes up. So all you're doing is drawing little arrows here, things like that. Q is equal. The voltage is going to go down. E is V over D. It's electric field is just voltage, potential difference divided by distance, a uniform electric field. And so since V goes down, then E goes down also. A little more space. And then U, for this one we're going to look at the CV squared, because C and V are the things that are changing. If we use the Q, Q is not changing, so we might get kind of a different answer there. But here, as you can see, the kappa ends up on the bottom, and so the stored energy also goes down in example 1. But example 2, here it's going to remain connected. It's remaining connected, so the thing that's remaining the same is the voltage. The battery is going to maintain the potential difference in the circuit. And so in this case, so the capacitance, since we insert the electric, the dielectric, this goes up, but the voltage remains the same. Right, Q equals CV. That means that if C goes up, but V remains the same, then Q is also going to go up. And then the electric field is also going to remain the same, because the electric field just depends on potential difference in distance. So this is going to remain the same. And that should ring a bell from electric field. It doesn't matter what material it's going through. If it's an insulator and not a conductor, the electric field is going to remain the same. Okay. But the potential energy goes up. If you look at the 1/2 CV squared, then what you end up with is a higher C goes up, but V remains the same, and so the stored energy goes up. Okay, so let's take a look at example 3. A capacitor with air is connected to a 50-volt source, charged and then disconnected. So it's disconnected, so what's staying the same? The charge. Charge is staying the same. The space between the plates is filled with Teflon, and kappa of Teflon is 2.1. As it says, find the new potential difference across the capacitor. So let's see, Q is CV, C naught V. So then it's going to be kappa times C naught V. That's going to be the potential difference. So now the voltage, so Q is going to remain the same. This C naught is staying the same. Kappa is the thing that's changing. So V is going to be whatever. It's going to be Q naught over kappa C naught. So that's just V naught over kappa. So the initial V is 50. It's a 50 volt source. That's how much charge. That was the potential difference across it initially. But now that's going to change when we insert this thing. Over 2.1 gives you 23.8 volts. So it's a game here of looking at our equations and saying what's staying the same, what's changing. Right. So then dielectric strength. So every dielectric has a strength to it. In other words, how much electric field it can stand before it breaks down and loses its dielectric properties. All right, so let's move on to example 4. We have a parallel plate capacitor. It's 2 by 3, separated by 1 millimeter of thickness. Find the capacitance, and then what is the maximum charge? What is the maximum energy that can be stored in the capacitor's electric field? This is our equation. Now it's filled with paper, so we can look up kappa for paper. So this is going to be 3.5 is dielectric constant for paper. And then epsilon naught, 8.85 times 10 to the negative 12th. And then the area is going to be 2 centimeters by 3 centimeters. So I think it comes out to 6 times 10 to the negative 4th square meters. And separated by a distance of 1 millimeter. And so then that is 1 times 10 to the negative 3rd. I think this comes out to 18.6 times 10 to the negative 12th farads. Okay. B. See, the question is, what is the maximum charge? So Q max equals C times V max. And the way we get V max is from the previous thing. We find 1600, that's the dielectric. We find that from the chart. Chart somewhere, kilovolts per millimeter, so 16,000 volts per millimeter. So this is going to be, this number times 1600. So this gives us 2.98 times 10 to the negative 7 coulombs. And then U max is going to be, by the way, this is 16,000 because it's 16,000 per millimeter, and this is 1 millimeter thick, and so that's the maximum voltage this one can have. If this was 2 millimeters thick, then this would be 8,000. So just keep that in mind. All right, so this is going to be, let's say, 1/2 CV squared. We know Q max, we know C, we know V max, so we can do this a bunch of ways. Whatever way you do it, I think you're going to get 0.02338, or it might be 0.00238 joules. Honestly, I'm not sure. I've got both answers written down. I don't know which is which. The important thing is the problem-solving process anyway. Okay. Example 5. Capacitor, they give you the surface area and the thickness. So same kind of thing. This process is the same. And so when you do this, right, kappa here is going to be, you look up for polystyrene, and it's 2.6. So this is 2.6. What we had before, A is the same as 0.1, which they say, and then 25 times 10 to the negative 6 goes here. When you plug those numbers in, you get, I think, 92 microfarads. No, sorry, that's an N. Nanofarads. 10 to the negative 9. So Vmax then will be that dielectric strength number for polystyrene, which you can look up. It's 24,000 per millimeter. So you do 24,000 volts per millimeter, and then divide it by this, or rather multiply it by 2.5 times 10 to the negative 6 meters. And so this is going to end up giving us, and if it's meters, so let's say volts per, let's say 10 to the negative 3 meters. And I think this works out to be about 600 volts. See the maximum energy, whatever way you want to do this, 1/2 CV squared, because we've got C and we've got V. We didn't calculate Q, so this is probably the best way. 1/2 of this times this squared, and I think that gives you 0.017 joules. So I'm going to hold off here because this is already 25 minutes. We've got a ways to go with some other examples. So there'll be part 2 of this video.